Welcome to Dunway Mechanical Engineering. We're doing a heat transfer problem from 975 in Bergman. This problem where you have some fluid at 35 degrees C transporting through some tubes through quiescent air at 25 degrees C, and we're asked to determine which of these four tube shapes of the same cross-sectional area would we want to use to do that, to minimize heat loss by convection. And we're told what correlation to use. There's a Rayleigh correlation, assuming the boundary layer does not separate from the surface, and we have an average Nusselt number that's 0.52 times a Rayleigh number to the 1/4, and our characteristic length is the length of the travel of the fluid in the boundary layer across the surface. So if we're looking at this, right, if we have some quiescent air out here, T infinity, etc., we're going to get some air flowing over these shapes, and so we're going to have essentially half the perimeter of each of these shapes as our characteristic length. Alright, so let's take a look. What do we know? So we know four shapes. We know quiescent air properties. And let's see, we know we're going to use the Rayleigh correlation. With that, what are we trying to find? We need the shape with min q prime, right? Not necessarily, I spelled that wrong, h bar min, right? We could end up with a smaller h bar but have a bigger perimeter, so that we'd end up with more heat transfer from that shape. Alright, so we got our schematic here. I'm not going to draw that. I'll just add to it. We have TS equals 35 degrees C, T infinity is 25 degrees C, and we have these various pieces here. Alright, what assumptions are we going to make? Well, we're going to assume steady state. Told nothing about time. It's probably a good assumption. 2, we're going to assume ambient air is quiescent. IESCNT. No radiation. And then all shapes have the same area. Cross-sectional area. Which they tell us in the problem statement, but we'll write that down as well. So then if we go to our properties, in the back of the book, we need a few things. So from air, we're not told what the fluid inside of this is, but since we're at steady state, we can assume that we're close to that surface temperature being 35 C. So we're going to look at air at 300 Kelvin. It was really 298.15, but we'll call it 300. So we have nu. Doing that lookup, we get 15.89 times 10 to the negative 6 meters squared per second. Alpha, 22.5 times 10 to the negative 6 meters squared per second Kelvin. Meter. Did I mix this up? Nope, those are the same units. Okay, great. K. Thermal conductivity, we get 0.0263 watts per meter Kelvin. And our Prandtl number, 0.707. And finally, thermal expansion, you can use the ideal gas law, 1 over TF. Alright, So we have that line heart correlation. What else are we going to need here? We're going to need to find our... We're going to need to find a few things, right? Let me rewrite the line heart correlation again for just a moment. 0.52 Rayleigh number based on L to the 1/4. Alright, so there we have that. We need to minimize Q prime, which is going to be H bar L times P times TS minus T infinity. It's going to be the same for each shape. P is going to vary, H bar is going to vary, so that's what we're going to look for. Alright, so let's find our lengths. Well, let's start first. We can get our Rayleigh number in terms of length. Looking back at our Rayleigh number definition, we have G times beta times delta T over times L cubed over nu alpha. So we get 9.81 times 1 over 300 times 10 Kelvin times L cubed. That's going to be meters cubed. And then over 15.89 times 10 to the negative third, negative 6, excuse me, times 22.5 times 10 to the negative 6. And so if we carry that through, we get 9.137 times 10 to the 8 L cubed. It's going to be our Rayleigh number, because all of these properties here are independent of the shape that we pick. Right? So L cubed is the only thing that we have different there. Excuse me, so that will depend on our shape. H bar then equals the Nusselt number, right, times K divided by L times our Rayleigh. Sorry, I got that mixed up a little bit here. We were subbing something else in there. So what do we have? We've got our Nusselt numbers here. .52. This Rayleigh number, 9.137 times 10 to the 8 L cubed, and that equals H bar L over K. H bar L is going to be 0.52 9.137 times 10 to the 8th L cubed times K, and K was 0.0263, and we're going to divide it by L, so we get that going to square. So H bar L is going to be 2.378. Oh, I forgot to the 1/4 up here. 1/4. I screwed that up. To the 1/4. This is still L. And so we get L cubed to the 1/4. Okay, so we're going to end up with that times L to the negative 1/4 down there. So there we have it for our general arrangement. Now we just need to find L for these, fill those in, and go through it. So looking at these guys, half our perimeter. Well, what do we get? If I just take from here to there, I get 50 millimeters for that guy. This one is 40 millimeters, same as this one, 40 millimeters. This one gets a little more tricky, right? My whole perimeter, P, is going to be pi d, so my half perimeter is going to be pi over 2 times d, which which is 22.56. So what do we get for that one? We end up with 35.4 millimeters. So we're going to fill those in. We're going to convert them into meters, right? So this is going to be 0.05 meters, 0.04 meters, 0.04 meters. So we should get the same results for both of those guys. And this is going to be 0.0354 meters. Alright. So filling those in, shape 1, 2, 3, 4. Our L is going to be 0.05, 0.04, 0.04, 0.0354. And so then filling that into here, H bar sub L. This works out to be 5.03, 5.32, 5.32. This is 5.48. So if you're looking for the minimum heat transfer coefficient, we would pick this guy. But we still need to multiply by our length, right? So Q prime is going to be P. I should maybe put that out there. 0.0. Oh, that's going to be 0.01 actually. Meters. 0.08, 0.08, 0.7078. So Q prime equals H bar L times P. So I get watts per meter. Alright, so I'm going to get 0.503. That's going to be 426. 426. This last one is going to be 0.389 when I multiply these two together. And so it looks like we're going to get this one for the winner. That's 0.389. So there we have it. So we find that, and that's going to be our value. So maybe, unsurprisingly, maybe surprisingly, I don't know. Depends on what your intuition was. Each of these are the same areas. This one was our winner for minimum heat loss due to its smaller surface area compared to these two. And it ended up having the highest heat transfer coefficient, which is also interesting. So as we go from there, I'll leave this last bit to compare to the sphere. So that's from the Churchill correlation. Pull that up and work through that, and you should be able to compare this result to that value. Thank you.